Okay. So today we are continuing our lecture and class activities into Module 5. And let's go ahead and we'll share screen over to this guy. And I'll drag our stuff up here. We get going because I want to look at the course content list of assignments and just remind us that we're working on Module 5 that's due here on March 27th. It is not this coming Sunday, right? Just for those of us who missed class on Monday, we're looking at the due date for Module 5 is the 27th, according to our list of assignments. It's our current assignment, okay? Okay.
We don't have anything really new to the council.
Right, but this stuff's kind of challenging, so I would definitely, we'll get going on it, and also use tutoring as necessary, tutoring services in the library. Okay. All right. This guy. Yeah, Module 5. So here it is on the screen. And you come down here. So I presented this on Monday. I know, it's okay. I'll recap it now. So here's Module 5, rational expressions, and rational expressions is these first three sections, 6.1, 6.2, and 6.4. I have a couple more problems to do in 6.1. Then 2 and 4 is more. And then we go back to chapter 2 on purpose, and we pick up literal equations as the last skill. Okay. All right. So let's head over to or some. And we'll load our book. There's a couple more problems in here that I wanted to do with you. This is the stuff that we covered. If you want to read it. We covered all this stuff on Monday. And we did that first example. Then we did example 3, which was simplifying. The first example was domain of a function. Second example was example 3 for simplify. And today, I want to kick us off with multiplying. Here's the next thing. So we had to learn how to simplify a fraction before we can do other arithmetic operations with rational expressions. And again, rational expressions are what? A fraction that's got variables in it. But we can't call it a fraction when it's got variables in it. Fractions are just a quotient of two integers or a ratio of two integers. As soon as you got a variable in there, you don't really know what that number is. And so we call them rational expressions, but they look like fractions. They behave like fractions. It's just there's additional considerations to make when you have variables inside of a rational expression. A rational expressions, basically got a fraction in it with variables. Okay, so let's go to example 8, and we'll kind of demonstrate multiplication. So this is like we're starting to do the arithmetic of it, the arithmetic of rational expressions. So arithmetic is like add, subtract, multiply, divide. Simplify first, because you have to know how to simplify a fraction. We did that already on Monday. But now it's like, before I can do add and subtract, believe it or not, multiply and divide are critical, knowing how to do that. Then we're going to go move on to add and subtract. So I'm going to copy this problem down, and we'll bring this back on the screen. Okay. So we're picking up a remainder of section 6.1 first, and then we'll move into 6.2 today. So here we have 7x plus 7y over 4ax plus 4ay times 8a squared x squared minus 8b squared x squared over 35 ax cubed minus 35 bx cubed. Make sure I got it copied correctly. 7x plus 7y over 4ax plus 4ay. 8a squared x squared minus 8b squared x squared, 35ax cubed minus 35 bx cubed. Okay. So let's start this guy back up now. We'll go to this. Okay. So the instruction for this is multiply for this example. Multiply. So sometimes you have to think about what you're doing to go, all right, no, do they literally mean multiply? You know, how do you usually multiply fractions? Straight across, right? You have two fractions, it looks like two fractions with multiply in between. It's true. But sometimes, you know, when we do fractions, we multiply straight across. Do they really want me to multiply this whole thing times this whole thing, the two numerators? And then this whole denominator times this whole denominator? No. Believe it or not. I mean, it's the result of this and why the simplify skills are necessary was because always try to simplify your fraction before you multiply. It's a strategy. It's like, yes, you are multiplying, but can you simplify as you go? That's the trick to not getting this to be super complicated. Okay, so let's see what happens. When you multiply two rational expressions, here's the first rational expression, here's the second one. First, put multi-term, like this numerator's got two terms in it. Guys, watch me up here. Look, guys, do this with me up here. Close your laptops, please, and do this with me, please. Attend math class. All right, unless you're taking notes, that's fine. But please don't work on papers or anything, okay? For somebody else's class or whatever. 4ax plus 4ay, these are this is two terms and this is two terms. This is two terms in this numerator and this is two terms. When you have multiple terms, capture them in parentheses before you begin. Then you times straight across and join them with a single fraction bar. So there's multiply between these two numerators, between these two denominators. From here, instead of literally like foiling, like, you know, FOIL between these two binomials, don't do that. From here, we're going to factor and do the simplify thing. As if this was like now, this is something to give us and just said simplify. So what were the two steps of simplify that we said on Monday? Factor completely everything. Now there's 4 polynomials I got to factor in one problem. Factor them completely and then divide out common factors. That's the approach to multiply. Guys, we're going to do this up here, right? Okay. factor this guy. Sometimes it helps to do this. Block off everything that, because you got 4 polynomials. This is just a trick. You can do this mentally, or you can do it physically. Like literally block off everything in your mind except one of them. So I see that maybe there's a GCF, right? Seven can come out. X plus Y. Does that look good? Like if I factor out the 7 from both of these terms, what the trick is now is slash out the old thing and replace with its factors. See that trick? Factor and slash out the old thing. In the end of this simplified, the factoring step, you won't look at anything slashed out anymore. You'll just look at this stuff that replaced it. This is live, these 2 factors, this is like gone. And then move on. This is the trick. Now focus on this guy. Any GCF in here? I'm doing GCFs in red. There's an 8, yeah, and x squared, 8 and x squared, Cheyenne. So take it all out, 8x squared. What would be the remaining polynomial? There's an a squared, right? Minus b squared. Does that look good? I mean, just like if I redistributed this, 8x squared to both of these, I'm good, right? I get this back. Is everyone, you guys are checking me as I go, right? Then slash out this original because you're done with it. Now, can I go further? There's a difference of squares, isn't it? So can I replace this now with a plus b times a minus b? Isn't that how a difference of squares factors? I mean, it's really like you're almost looking at the formula for it. So slash this out. The other thing you can do is factor completely means, couldn't I break that 8 down to 2 times 2 times 2? If you want to do that, you can. Look, take this 8 and replace it with 2 times 2 times 2. What about the x squared? X times x. That's factoring completely. Is you can, if it helps you. Otherwise, you're going to do quotient rule to subtract exponents for any x's that are in the denominator. Sometimes this helps students to break it down, everything completely down to small objects. You know what I mean? You can look at. All right, so the numerator is completely factored. Only the things that are not slashed out are live. So you're keeping an eye on this. I made it purple. Here's the fraction bar. I also did this. I left room by writing the original problem in the middle of the piece of paper. And I just kept factoring above it. And now I'm going to factor below that fraction bar. I'm going to factor the denominator below it. This helps you to not rewrite the problem over and over too many times. It saves time, this approach, okay? All right, what do y'all have for a GCF down here now? A 4 and maybe what are the factors in common? 4 and a, good. So what would be the remaining polynomial here? 4a times x. Does this look good? And then 4a times positive y. Does that look good, guys? Slash and replace. I could break this 4 down to 2 times 2. Slash the 4 out. Anything not slashed out is live in this denominator. Then move on. So here's another binomial. What do you see in here? Between this term and this term. Right, Cheyenne? 35 can come out. And what about the x cubed? Isn't that all these common factors? And then what would be the remaining polynomial? A minus b. Good job. Slash all this out. We're replacing that whole binomial with its factors. Okay, what about 35? Can I go 7 times 5 is in that multiplication table. And then x cubed is x times x times x. Slash that out. Now anything not slashed out is live. So we just factored this rational expression completely, and it's like a mess, but as long as you make it legible, you'll be okay. We factored completely. Here's our fraction bar. Now I'm looking for common factors between the numerator and denominator. Here I see a 7. I'm looking for a 7 down here. See it? So I go, anything divides into itself and gets replaced with ones. Then I just move on. My system is to pick up the upper left factor in the numerator and move to the right, to the next one. Is there an x plus y down here anywhere to match with this one? You seeing this? That, isn't it? So anything divides into itself and leaves ones behind. Then the next live factor is 2. Here's a 2 to match with it. See, it's like I'm just doing open season on common factors, right? Then here's another 2. Is there another 2 to match with this guy? Yes. Every time we do a slash out, they're replaced by 1. Then I see this 2, but I don't see any other 2s. Do you guys? Because it is visually like overwhelming a little bit, right? When you do this approach, this factoring thing. Okay, so I don't see another 2 down here to match with that 2. So that's going to remain in the numerator. Here's an x, here's an x. Here's another x. I can take out the second x down here, replace with ones. Here's an a plus b. Do you see an a plus b down here? Anywhere? No, right? So a plus b is going to stay in the numerator. Then here's an a minus b. Is there an a minus b down here? Yes. Slash and replace with ones. So now I know I got a 2 and an a plus b up here. What do I have down here? Here's an a by itself. Here's an x by itself. And a 5. Very good. So now let's rewrite this whole expression cleaned up with only the factors that remain. In the numerator, we've got a 2 and an a plus b. In the denominator, we've got, if we put them in order, 5a x. And I think that's everything, right? So 2 things about the answers, the way we format answers. This is a correct answer. Response, you know, if you think about it as a test, in factored form. Factored form for these problems is when you leave things unmultiplied, like you don't actually remove these parentheses. You know what I mean? You leave the numerator in factored form. Factored form is like, isn't the goal of factoring something times something? So this is factored. The convention is to leave it like this. But there's another look of it, is what if I do go ahead and distribute the 2? What would I get? I'd get 2a plus 2b over 5ax. This would be an alternative answer. This is also correct. Correct response. Now it's in, what's the P in PEMDAS, right? PEMDAS is the way we simplify things. So P in PEMDAS, this is simplified form. Factored form, you leave it unmultiplied. Simplified form, you perform all the multiplication. So there's 2 correct answers. My math lab usually does factored form. This is usually my math lab answer. But read the formatting. You know, the thing under the answer box in my math lab, always read the purple formatting requirements before you click check my answer. Okay. All right, let's see what your textbook did. A lot of the similar stuff. So they show the 2 versions of the answer like we did. but they just don't explain what you're looking at. Yes, sir. Alex. Like that, Alex? So again, that's factored form because the two and the two hasn't been distributed. Here's simplified form. Okay. Okay. Let's look at number 9 now. Alex, you got this one? Here. Excuse me. No, at the end of class. Okay, next guy. Yes, sir.
What about if in the denominator, we'll have a number, we'll have to multiply both numbers, like, let's say that,
If you had a second number,
yes, in the bottom.
yeah, like a 5 and a 2 multiplying. Numbers always get combined. It's like when you have a polynomial and something outside, that's when they leave them unmultiplied for factored form. But if you have two numbers like right next to each other, like 5 and 2, I would multiply and make them 10. Great question. That's a great question. Okay, so we did multiply operation. Now we're going to do division. Copy this guy down. And then I'll move this out of the way, okay? So here's example 9. 4x squared minus y squared over x squared plus 4xy plus 4y squared divided by 4x minus 2y over 3x plus 6y. Okay, make sure I wrote it correctly. 4x squared minus y squared over x squared plus 4xy plus 4y squared divided by 4x minus 2y over 3x plus 6y. As we talked about like a lot in class, please definitely check what you've written down before you proceed on a problem like this. Because, I mean, it's painful to have to do this much work twice. Okay. So we're doing, the instruction for this is divide. It looks like two fractions, and you treat it like two fractions. That with division. So what's the rule for dividing fractions? Keep. For which one? The first one or the second one? Very good, Priscilla. So keep the first one the same. Change division to multiply Ellie, and then flip, make the multiplicative inverse or reciprocal of the second one. So that trick still works for us. So here it is, look. Keep the first one exactly as it came to us. Change division to multiplication. Then flip this, it's informal, but it's, the way that people remember it. Flip the second fraction, turning it to its reciprocal or its multiplicative inverse. So keep the first one the same. 4x squared minus y squared. And see how I'm leaving room here above it to do my factoring. Over x squared plus 4xy plus 4y squared. So we kept the first one the same, first rational expression, change now division to multiply. And now we're going to flip this guy. Make the denominator the numerator. And make the original numerator the denominator. And now it becomes just like what the problem that we just did. It's just everything's the same after this. You just have to remember to do this part. So Draw a big fraction bar all the way across, but first capture all the numerators and denominators because they're all multiple term. There's multiple terms in them. They're polynomials, more than one. They're all, I've got 3 binomials and 1 trinomial, and then connect them all with multiply if you want to have that visible. Okay, now we start factoring. So you can mentally block off the ones. I won't do the paper thing for the sake of time. I'm mentally just focusing on one of them. Any one that you want. So what do I see out of here? I don't know. I don't see a GCF. But what do we have here? Looks like a difference of perfect squares. Right? 4x squared, that's a perfect square. Y squared, that's a perfect square. It's a binomial with the difference between subtraction. So the square root of the first one is a, 2x. The square root of the second one is y, that's b. A and b, 2x and y. So I go 2x plus y, 2x minus y. Square root of the first term is a. Square root of the second term is b. A plus b, a minus b. I use the special factoring formula for that one. Okay, anything in here? Between 3 and 6 is a 3, right? And nothing else. 3 times x makes 3x. 3 times 2 makes the 6, and I need a y in here. And I slash this out and replace this guy with its factors. Let's come back to this one. Sometimes I do all the easy ones and then hold the hardest one for last. You know, I'm like everybody else, right? All right, so what about this one? Between 4 and 2, there's a 2, right? Good job. 2x minus y. Slash these out. Slash the original polynomial out. Okay, what's next? What's catching my eye about this trinomial? I don't see any GCFs to pull out. So I'm going straight to, this looks like a perfect square, and this looks like a perfect square. So A would be square root of that. Square root of x squared, x. What's B? Square root of 4y squared, 2y. A times B is x times 2y, right? X times 2y. What would that give me if I put it all together? 2xy. That's A times B, 2xy. Now double it. Times 2. What do I get? 2xy times 2. 4xy, I'm already. Is that our middle term? Yes, this is a perfect square trinomial. So it factors as A plus B, because I got pluses everywhere. That's the main plus to look at. It's going to factor as A plus B. A is square root of the first term. B is square root of the second term. Squared. That's a special factoring formula for perfect square trinomial where the middle term is positive. Now, the same as factor completely, I would take this binomial squared and expand it. X plus 2y is the base of this exponent, but I should see 2 of them. So we're expanding using the fundamental property of exponents to make it look, you know, like completely factored. This follows that idea of factor completely and break numbers down to the smallest things that they are. Okay, now we're finished factoring, so I keep my eye on this big old fraction bar. And then we just go to town on common factors. I just go from left to right. You don't have to do this, just make some system of your own. There's a 2x plus y up here. Is there a 2x plus y down here? Is one of these 2x plus y? Very good. But see how it's like an eye catcher? This one, it kind of, if you look too quickly, you go, oh yeah, if I flip these around, it's just like that. No, this is x plus 2y. That's 2x. This is 2y. You get me? There's nothing like that one down here. So I move on. 2x minus y. We have one of those down here. 2x minus y. What about this? That's a match, right? So we're keeping this one. There's nothing else like it, but this one divides into this one and leaves ones behind. Okay, now here's a 3 all by itself. Do I have any 3s down here? No, so we're going to keep that one. Here's x plus 2y. Do we have an x plus 2y down here? One of these, like these are identical. One of them can go away. The other one got to stay. Because that was the last factor up here. So when you go from left to right, very systematically, by the time you get to the end, you've compared all the factors in the numerator to all the factors in the denominator. You know that you're done at that point. And then whatever else is down in the denominator is just going to stay. So if we clean this up, what we have is, and the convention is do monomials first, then binomials, then trinomials, from left to right. That's why I'm going to write this one first. It's like a single term polynomial. Then I go to 2-term polynomials. And then if I had a trinomial up here, I'd do trinomials next, if I had them, but we don't. Okay, then down here, I'm going to go to the convention again in the denominator. Monomials first, the 2. Binomials second, whatever is remaining. And I think that's all we have down there. So this is factored form. It's correct, it's in factored form. If we distribute the 3 and the 2, we get 3 times 2x is 6x. 3 times y is 3y. 2 times x is 2x. 2 times 2y is 4y. And this would be simplified form. They're both correct. My math lab wants usually factored form. It's not just my math lab, it's a convention. It's a convention in math because factored form's got a future to it. It's like if this was part of an equation, factored form is more useful. Keep things in factored form because you may make the equation easier. For sure, I'm going to show it to you. We're going to get to that. So compare what we got now with what your book did. Bless you. Same thing. Right? It looks the same to me. You guys see that? That's always a good sign when what we do in class matches what they got in the book. Because they had forever to do it, but I'm doing under the pressure of the clock. You know, so it's like they had forever to. This is the 8th edition of this book. I'm sure all the answers are correct by now. Okay, that's the end of this section. As you see, that was like a long section, and that's why we're doing 2 weeks for this, because one of these sections is a little bit long. That's all 6.1 for Module 5. Okay, let's move on now to section 6.2. Adding and subtracting. What's that, Shane?
I answered it. What is it, 2.2?
Yeah, that'll be last. Good job. Okay, adding and subtracting rational expressions is our next section. So let's think about what we would do. This first discussion is kind of good, you know. Okay, let's think about this for a minute. See this like small pair of fractions right here. This now is adding and subtracting. If I want to add 2 fractions together, like 3 7s plus 2 7s, what's the thing about adding or subtracting fractions that's critical before you actually put them to combine them into one fraction? Are the denominators the same? Very good. So I go 7 and 7. Are they exactly the same? Then you can, what's the denominator of the new fraction? Do I add the 7s or do I just keep 7? Chris, right? Is that you, Chris? I can't see. Keep the 7. You don't do the addition for fractions, doesn't happen in the denominator. The addition happens in the numerator, right? As long as you make sure the denominators are the same, you keep, and when you put the two fractions together, that common denominator is the denominator of the new fraction. So they do. So they combine, they make the new denominator 7, and they add the 3 plus 2 in the numerator, make 5. Okay, what happens next? See 2/3 and 3/4? See this new set of fractions? And it's got addition, but this is also the rules for subtraction. This is what happens when I add or subtract two fractions and the denominators are different from each other. What do I need to calculate? It's similar to that. It's got a different name, but it's similar. The least common denominator. We have to calculate the least common denominator, then convert both of these to have that denominator. And it'll be the least amount of work that we have to do. The least common means the smallest number that both of these can divide into. You don't even really know like that, but that's what it does mean. The bottom, yeah, we have to calculate the least common denominator of the two denominators. Well, there's a process I'm going to go through. It's a 4-step process for calculating least common denominators. We'll go through it together. For sometimes what people do, it works for this one, and you do get the least common denominator, but I'm telling you, it's not going to work. It hardly ever works for math problems. Is they go 3 times 4 makes 12. You guys ever done that? Like when you need to get a problem done really fast, you just take the denominators, you need a common denominator, and you just multiply the denominators. That actually is the LCD for these two. For now, I'm just going to go with that. So what would I have to do to 2/3 to make a fraction that's got 12 in the bottom? 12. I'd have to multiply this 3 by 4. But then I also have to multiply the 2 by 4. You can't just multiply the denominator and get 12. You know what I mean? You have to multiply the numerator. It's fractions when you convert them to equivalent fractions. They're like a little equation. Whatever I do to the bottom, I got to do to the top. You with me? Guys, look. Whatever I do to multiply the bottom to make the LCD, whatever that number is, I got to multiply the top by it also. And if you think about that fraction, when I times by the first one by 4/4, see what they're doing? What is 4/4? What does that simplify to? 1. So you're really, by multiplying the original fraction by 4/4, you're really not changing its value. You're just changing the look of it to achieve the goal of adding this fraction to the other one. You're really timesing by 4/4, you're timesing by 1. So you're not changing the value of that fraction, of this fraction, 2/3, but you're changing the look of it. So that's going to happen for us when we do this with polynomials as well. What are we going to have to multiply 3/4 by to make a denominator of 12? 3/4. This guy. What is that for? Need to be this 3 needed to be multiplied by 4. What does the 4 need to be multiplied by? 3. So what are you going to multiply the numerator by? Also 3. So this is just a reminder of what we do with fractions when they're numbered, real fractions with numbers only. So now they go ahead and multiply those straight across. And the denominators are the same now, right? 12 and 12. And then we multiplied straight across. You have 8/12 for the 2/3, and you have 9/12 for the 3/4. But if you re-simplify these, they'll go right back to these original fractions. That's what makes this allowable. But now now that they both have the same denominator, what's the new denominator? when you combine these two fractions. It's going to be 12, and the addition is 8 plus 9, right? So 17 over 12. And then you would have to simplify your fraction if possible. So that's the look of when we have to do adding and subtracting. They're showing two additions, but this same thing holds when the denominators are different. And if you had subtraction between them, you have to calculate an LCD when the denominators are different for subtraction as well as for addition. But multiplication, do we care what the denominators are? No, it's straight across. What about division? Do I care what the denominators are? No, it's keep, change, flip. So question.
So would that be the answer, or do you have to change it next time?
It's simplest form in this way. The reason is, like, what do I do? 12 into 17, 1, and then remainder 5 over 12. This, guys, leave this. It's a common question. I mean, it's a very good question. Is this simpler form, or is 1 and 5/12 simpler form? Which one's the better answer in math? This one. You know why? 1 and 5/12 has 4 parts. This one has 1, 2, 3 parts. That's the answer. Less parts in math, better answer. Simpler form. Less parts means simpler form. Most of the time, like 95% of the time in this class.
How's that?
1, 5 over fraction bar 12. Where this is 1, 2, 3 parts. One less part. Yeah, this one's got 3, the other one's got 4. But that is the answer to the question. This is simpler form than a mixed number. Very good questions, guys. They show a method of finding the LCD. They make a statement here of the process of finding an LCD. Mine's going to be slightly different, but we achieve the same result. You can use this process if you want. That's here on page 318, as long as you calculate the correct LCD. Okay. I want to do the next example because it's more illustrative of the 4-step process. Okay. Here's example 2. And I'll move this out of the way in a minute. So now we're into section 6.2. Our next section in module 5. And this is example 2. So in example 2, they show us 2 rational expressions, 7 over 2x or 12x y squared and 4 over 15 x cubed y. Make sure I got it right. 7 over 12 x y squared and 4 over 15 x cubed y. All right, let's go back now to this. Let's get over here and try to do it right. Right. The question that they have for this is find the LCD. Find the LCD, the least common denominator. Okay, first of all, I'll do the 4-step plan here with you. But the first thing to realize about the least common denominator is, what does the D in LCD stand for? The D in LCD, what does it stand for? Denominator. So really, when you're finding calculating, find also means calculate. You know, all the time when they say find, that usually translates to calculate. There's some kind of process involved to calculate it. So D in LCD means denominator. You focus all of your attention to the 2 denominators. So the first step in how to find an LCD is list. List all your denominators. I've got a 12xy squared, and I got a 15x cubed y. The next thing we do to find a LCD is we factor. I'm underlining the keywords to memorizing this process. It's list, factor, but I need to annotate this a little. Factor with exponents showing. Any exponents, I need exponents showing on everything, on every factor. So if I start factoring this guy, you know, like 12, and then the variables are already factored really, because to see how they've got, you know, the X has got an invisible exponent of 1. That's good enough for factoring for LCD. The 12 is what I focus on now, is maybe 2 times 6, 2 times 2 times 3. Here's where I have to reduce this now down to exponential notation, because I'm down to prime numbers now, right? 2 squared, 3 to the first. I'm just going to bring these guys to the bottom. X to the first, Y to the second. So there's every kind of prime number. 2 and 3 are prime numbers. Their exponents are showing. X is to the X, there's only one of them, so X to the first power, I write that in. Y to the second power. Every different kind of factor is showing with exponents. So I'm going to do the same thing. Really, it's just the numbers that need to be factored when you have monomials. So I got a 3 and a 5. And I'm already down to prime numbers, so I show their exponents. And then I got an X cubed. And this time, Y is to the first. Okay, now we're ready to assemble our LCD. So step 3 here is I want to include unique factors. Unique factors, one of everything different. So here's where I actually start assembling the LCD. So I start looking at all the different kinds of factors I have on the bottom of this, the green row for each of these guys. So like here's the 2 different kind of factor trees I have. See how 2's, the bases of the exponents are the factors. Let me write that in. Bases are the factors. The bases are the factors. So I go, 2's, are they in here yet in the LCD? No, 2's need to be represented. That's what you're doing. You're representing one of everything different. Are 3's in here yet? In here, in this blue thing? No, so I need 3's to be represented. And they're going to be times together because this is a multiple thing. And then X's, are X's in here yet? Like in this blue area? No, so I need X's to be represented. See, one of everything different, unique factors. X's, I'm leaving room because I'm seeing a 5 coming. See, Y is not in here yet. I need Y's to be represented. Y's are different from X. Then I hop over here. Look, see, it's because we have one of everything from this first factor tree. What about this factor tree? Are 3's already in here? Look, see that? So I don't put another 3 in. 3's are already represented. See what I'm doing? And then 5's, are 5's in here yet? No, here's where I throw the 5 in. I just left room because I could see it coming. Are X's already in here? Yes. Are Y's already in here? Yes. So then I've got one of every kind of factor. This is how you build an LCD the right way. And even your book that's the right way too, what your book shows. It's just, this is more broken down a little bit. Okay, last thing, step 4. I'm just going to show a new piece of paper. The last step in this. I want to apply the greatest exponents that I see from the factor trees on every one of these. The greatest exponents I find in the bottom row of these factor trees, the green factor trees, to each of these factors. This is the last step. Greatest exponents. So watch what this means. On 2's, What's the biggest exponent I see? Like 2's appear here. It appears to an exponent of 2. Are there any 2's in this factor tree? No. When there's no other 2 in the other factor tree, I grab the entire exponent and I put it all on this one. I need all of the 2. When there's nothing bigger or doesn't exist at all in the other factor tree, this factor, then the exponent that's showing in that one instance is what we use. Okay, now look at 3 in both factor trees, because I do have 3 to the first over here, and I do have 3 to the first over here. But the exponents are the same. When they're the same, I just grab one of them. When they're a match, I just need whatever that match is. On 5's, I only see 5's over here to the first power. There are no 5's in this first factor tree, so I use whatever that exponent is. Very good. On x's, look, here's where we like really have something to compare for the first time. We have x to the first in this factor tree, but we have x to the third in this factor tree. Which one's greater? 1 or 3? It's this one, the greatest exponent. And then y. Look, we have another version of that now. Watch this, guys. See this? On y's, I have y to the second in the first factor tree, but only y to the first in the second factor tree. What's bigger, 2 or 1? Say it, 2 or 1? 2, very good. The greatest exponent. The numbers, this is like Dylan's question. The numbers we want to expand and multiply into a single number. It's like that other thing last. So on 2's, I go 2 times 2, 3 to the first, 5 to the first, right? This is 4 times, I don't know, 5 is 20. 20 times 3 is 60. I just did a quick calculation. You know, I did commutative property is there to help you do multiply easier, whatever's easier for you, you know? So I knew that I'd get a 0 out of that. Then times that by 3. So say it's 60 x cubed y squared. This is the smallest expression. You know, I would box this. This is the LCD. This is the smallest, you know, expression, algebraic expression that both of these two original denominators would divide into. That's the definition of an LCD. But it's also for what we're going to use it for. The smaller I can make something, it's easier to handle and manage. It makes everything I have to do with that easier. I've got smaller exponents, smaller numbers. Because if I was to just take these two guys and times them together, what would I get? Just 12 times 15. What is that? Yeah. Like, you know how we said in those two fractions at the beginning? Why don't I just take the 3 and the 4 and times them together? In that case, it did give us the LCD. But what kind of number would I get if I just take these two denominators and times them together now? 12 times 15. I got 180. Moving forward, what would I rather deal with? 60 or 180? 60. It's just a smaller number. You see why we're calculating the LCD the way we do? This is the smallest numbers and exponents on variables that make all the rest of our work easier. Okay, so your book, you know, they do their process, their 3-step process. You know, I'm not a big fan of the way that they do it, but in the end, did we get the same answer? See 60x cubed y squared. See that? That's our answer, right? What are the 4 steps of calculating LCD? List your denominators, factor those denominators, include one of everything different. That's the unique step. Unique factors is in blue. And then raise each of those factors to the greatest exponent you find them. And then multiply all that stuff together. So it's an effective way to find an LCD. List, factor, unique factors, greatest exponents. It's the least number of words that I could make for you. I'm sorry. This would be the LCD, that if they told us to, okay, now next, add those together. But that's not part of this problem. We'll do that on Monday next week. But if they told us to add those together, see how what we're preparing for is if this was add or subtract, this guy and this guy, the two denominators are different. So for me to add them together, what do I have to do to both of them? Turn them into both having fractions with this as the denominator. Turn both of these fractions into new fractions that have this as the denominator. Then when both of them are the same denominator, we add the numerators. That's where one of the uses of this LCD. Another use of the LCD is what we're going to find in section 6.4, look ahead, is if I have rational expressions inside of an equation. Think about this. When I have fractions in an equation, what's one of our strategies that we do before we start solving? You multiply the equation by the LCD, and it eliminates all the fractions from the equation. It's the other use of LCD for us in this class. Use the LCD to add or subtract two fractions that have different denominators. And then the other use is multiply every term of an equation by the LCD, and it eliminates all the fractions. In this case, all the rational expressions from the equation, makes it easier to manipulate. Okay. All right, my friends, that's it for today. Please push into a little bit of just finding LCD in your homework for all the problems that come from 6.2, and then stop. Don't do the actual add and subtract problems in 6.2 because I need to do some examples for you next week.
What did we do on last week? Did that on Monday?
Just Monday.
Yeah, from Monday.
It's in your lecture notes. I'll show it to you in a second. Thanks, everybody. Have a nice weekend.
Oh.
That was it.